Hello and welcome to another edition of our lessons in microelectronics. We're going to be still focusing on our helpful tools series. We're going to go ahead and continue that. Along with, we've already done some AC analysis. That was the last video. Now this video I think I'm going to be showing you how to get models and from different manufacturers and import them in, because a lot of the models that you have with LTSpice are obviously linear technologies, since linear technology creates and makes LTSpice. So what we're going to do is I'm going to show you how to pull in third-party to LT. Basically, analog devices is where we're at right now. This is the one I've chosen for this video. But many other places, ST Microelectronics, On Semiconductor, Fairchild Semiconductor, just pretty much almost all manufacturers will have modeling of some sort. International Rectifier, Infineon, all those different manufacturers, TI, everybody will have simulation models. And what we're going to look at today is some of those models from analog devices. One in particular is we're looking at an op-amp model. So let's look at the OP196. That's one that just comes to mind. Type that in, we'll get all the specifications about the OP196. You can get the data sheet, as well as some other stuff. And what we're going to look at is down in here, you see there's one thing called SPICE models. If you click on this, it's going to take you to the SPICE model of this. Now, the one that I'm using is this OP196 SPICE Micromodel Rev A, which is this one. I haven't really used the G one. I'd have to open the model file and see what's different about it. But for what we're doing, the first one will be just fine. So you'll just click on that and download the file. Once you've downloaded the file, we'll bring up LTSpice. You can actually open it. It comes out as a .cir or circuit file. And when you open it, you'll basically get all this stuff. Now there's a huge explanation on how to actually build these models, but for all intents and purposes, this is all the information that you need. And if you notice, this is the subcircuit directive, which subcircuit, when you declare that, then you declare the pins. These are the pins. As you can see, it says this is the non-inverting pin input, this is the inverting pin input, and then 99, 50, and 49 are the positive supply, negative supply, and output. Now some of you are like, why didn't they just go 4, 5, and 6, or whatever, 1, 2, 3, 4, 5, or whatever? It's due to how they set up their model and how they've numbered their nodes inside the model. I may get to, I don't know if I want to go that far, but I may go into at maybe the very end of this LTSpice helpful tool thing. At the end of the LTSpice tool, I may give you kind of a window into how to create models and how that works. And basically, for those of you that have messed with older versions of PSpice, or the older versions of like OrCAD and things like that, which I think OrCAD now owns PSpice. I don't know, I could be wrong, but anyway, you didn't have a graphical interface. How we have like a GUI where we can throw down resistors, or throw down capacitors, or throw down whatever we want. Well, back in the day when Berkeley Spice was first released, you didn't have that luxury. You had to tell it everything, like by words. It was almost like those of you who've written Verilog or VHDL. It's kind of like that. You literally have to say what nodes you're numbering. So if you wanted a resistor, if you just wanted, like, let's say a simple circuit like a voltage source and a resistor, and you were just going to connect those up like this. I'm doing a horrible job of it. You're just wanting to connect, and that's what you want to do. I did that really fast with this, but you would actually have to label V1, and then that's connected to node. Let's say we'd label this 1. R1, pin 1 would be connected to node 1. R1, pin 2 would be connected to node 2. Node 2 would be connected to ground, as well as the minus of V1 is connected to node 2. And see, you'd actually have to type all that in, type all what all that is. And so If you have very complex circuits, you would end up, pretty much drawing it all out on paper, labeling all your nodes, labeling all your voltage and resistors, capacitors, inductors, everything, and then you have to sit down and basically formally type it all out into directives for then the SPICE engine to run. Well, that's basically what you do when you create a model. If you create a model of a part, you're basically defining every single little piece. See, here's different resistances, different capacitances, there's even some diodes modeled into this, all kinds of different things, and these are all your node numbers. Well, anyway, I'm not going to get, I kind of got a little farther into this as I wanted to. For all intents and purposes, it just kind of is what it is. What we're going to do is there's two ways of dealing with a symbol. Now, since this is an op amp, they do have, in your symbol list, if you type in OP, they do have two generic op amp symbols. One is without supply rails, the other one is with supply rails. Now ours will be with supply rails. The reason it is with supply rails is because remember back in our deal we have the supply rails, positive negative supply. So ours will be using that one if we wanted to use that one. Now another way of doing this is if, let's say, we didn't have that op amp symbol, we had to create a symbol. What you can do is highlight the name of the subcircuit, right click on it, and you'll find something that says create symbol. And what this will do is this will automatically generate a symbol for you. Now it will not be the IEEE symbol, I guess you would say. So the like this. It won't look like this, where it's the nice op amp symbol with plus and minus stuff. It will be a square, much similar to, maybe something kind of like those. How it's a square and then the pins are numbered. Now it doesn't have any of this fancy stuff inside. It's just going to be a block with the pin labels 1, 2, 99, 50, and 49. That's what it's going to have. And to show you that, I'm going to go ahead and do it. Create symbol. It says that wish to automatically create a symbol that will net list against the subcircuit and her 5 ports. Yes, we do. We want to go ahead and create it. And see, there it is. So if you notice, 1, 2, 99, you got to remember, 1 is non-inverting, 2 is inverting, 99 is positive, 50 is negative, and 49. 50, 49. Now, what this does is this is just the symbol file. To actually use this, it saves the symbol file in auto-generated folder inside of our library. So if we were to go back here, click on our component library, you see how there's these things, anything in brackets is a folder, okay, is a folder. So we go to auto-generated, if we double click on that, we'll get, it looks like I've auto-generated a max 4073 in the past, but there it is, OP196, and there it is. And to go up one level is what it's telling you here. You can either click this up one level, or you can double click on the dot dot. It basically follows basically DOS, the dot dot, CD dot dot type stuff. But anyway, and then you click OK, and now we can place it in our circuit. Okay. But since this nomenclature is the same, it goes inverting, or it goes non-inverting, inverting, then positive, then negative, then output. That's very important, the order of these. Since the order is like this, we can use our symbol, I gotta go up one level, our OP symbol. Oh, why is this doing this to me? Op amp. Oh, okay, I see why, because it picks the OP, op amp. I have to actually type op amp now. Now, for those of you that want to know where this is stored, my computer here installs x86, we're going to grab LTSpice, and then it'll be in your lib, or lib, and it'll be under symbol. Okay, symbol, auto-generated, and there it is. There's the actual symbol file that is created. See, OP196 ASY, there it is. So if you ever want to delete it, you can delete it, or remove it, or whatever you want to do with it. But for all intents and purposes, we can close this. And same with this, we can close this. Like I said, now, if you have this order, non-inverting, inverting, positive, negative, and output, if you have this order, that opens you up to be able to use one of the symbols, the op-amp symbol that's generic, that's already here. Whoops, wrong one. 2. Op-amp 2. So, now we have this. Now, the only problem is that if you right-click on it, it basically gives you this screen. This is a little bit different than what we've seen before. It gives you basically the complete symbol attribute editor. All components have this. Let me grab a diode and show you this. Just in case, if when you right-click on a diode, you can say pick new diode, and it gives you a list of diodes to choose from that are common manufacturers like onsemi, Philips, Vishay, some different companies where, but let's say yours isn't in here. You can perform this, your model that you download, say you download one from onsemi that isn't in here. You can do the same method with these, and I'll show you in a minute. You can actually pull up this same box and do what I'm about to do. I'll show you that in a second. Let me get rid of that for now. What we're going to do is we're going to pull this up, and if you remember, in fact, let me get that back up here. No, not that. The circuit. We need the name that we're going to type into one of our attributes has to be exactly what the subcircuit name is. So what we're going to do is we're going to go ahead and copy that. And when we right click on this, where it says value, we're going to replace that with the name of it. Okay. Now, we're not done yet, because if we were to run this, let's say, I don't know, let's build something. I don't know. Here, let's do a comparator or something. Even though it's not always necessarily good to use an op-amp as a comparator, but for intents and purposes, that's what we're going to do. Or just something. I haven't built one of these in a while, so I might be doing it wrong, so forgive me. I believe this might be right. Oh no, that's not what I wanted to do. I need a reference of some sort. Take this off and we'll give it a reference. Vref. So we'll call it, put that there. Voltage, put that over there. Duplicate this, put it over here. We'll make this 5 volts. Let's say. And this can be, I don't know, 100. And this would be 1. Sure. Why not? This can be, I don't know, let's make that, oh, doggone it. That can be VRF too. Why not? Why not, since we're just doing this for giggles? Okay, there's something. Okay. The out. Okay. Anyway, there's some sort of a mess of a op-amp. Okay, now, what we're going to do with this now, like I said, we are not done. If we go ahead and run this, it will actually give us an error and say that it can't find the simulation file, and that there's something wrong with it. What we have to do is we have to link the library to this using what's called a dot command. If you come up to here, this .op or spice directive, you can now type in any command to send to the Spice engine. So in our case, what we're going to do is we're going to tell it where to look up our library component. So we need a .lib for library. We're going to hit OK. place that down there, and then once we placed it, right click on it again, and now you'll have the browse option because we've declared a lib directive. So you hit browse, and now is where you'll find there it is, op196. Browse to your op196.cir and hit OK. And now it knows where to find this op196. It knows that it is in this library. Now they are linked together. So let's say this is, I don't know, 2 volts. This should be low. Let's do, I don't know, 20 milliseconds. Output. Yeah, it's 1.3 volts. Now if we have like 8 volts or something, we should saturate. Yeah, more or less, something like that. So our comparator works, so to speak. So if we have 0 volts, it saturates to 0, and then if we cross our threshold of 5 volts, we get 6 volts or whatever, it should flip to a high, and it does. It flips to saturation the other way. So there we go. So our model successfully works. It successfully does what it's supposed to do. So anyway, that's basically how you import your models in. There's 2 different ways. There's the, of course, I hate that it does this. There we go. Okay, and but there's 2 ways. You can take and you can do the right click and choose create symbol if you don't have a standard symbol that this fits into. You just have to, the main thing, like I said, you have to just make sure the pin numbers are correspond. So even if you create your own symbol, which you can, you have to just make sure your pin numbers correspond. So if you get a different MOSFET that maybe the first one is drain and then gate and then source, but then you may get another manufacturer that goes gate drain source, not drain gate source, but gate drain source. Well, then where you've placed your gate pin in your symbol won't be in the right spot. It'll be on the drain or something, essentially, because the 2 models are different. So always make sure your pins correspond to where the pins are, on the symbol. Make sure that they're in the right spot. And if they are, then you can just straight away use the symbol. Or you can either modify the symbol, like I said, I showed you that that directory structure where that is, like I said, and if you ever wonder where it is, it's right here. It'll tell you it's in program files, LTC, LTSpice, LIB, and then in symbol is where all this stuff is. And you can always go in and save one as something different, and then tweak it if you need to. Move pins around. If they're the exact same, it's the right symbol for the part, but the pins are different, then you can just go in and save it as version 2 or something like that, and then tweak it, move the pins around, or whatever you got to do. But make sure the pins line up, and then you can use a ready-made symbol already in the library. Or you can create your own by right-clicking on the name, make sure it's in the subcircuit name, and choosing create symbol. And then you can create a symbol from that. So that's basically what's it from it. I may do one more from another manufacturer just so you can see something else. I wasn't planning on it, but just so you can see it done, I'll grab another one. Let me go to International Rectifier. We'll grab just anything. Automotive. Well, we'll do DirectX. Why not? DirectX. Oh, blah. Sure, this one looks fun. Okay, so look at this guy. He's got 20 volt max VGS. He's got, what else does he have? What is his current? He can pull 64 amps of current. All right, he's pretty good little guy. Now, if we look around on this plate, on this, we should be able to see. Just gonna find. Let's see if we can model. Well, it looks like this one doesn't have a model. And sometimes when you run into this where they don't have a model, you may have to actually submit a request for a model. Let's see if I can get one that has a model. Get one that has a model. That one's, no. Those might be so new that they don't have one. I'm going to pause for a second and find one real quick. Okay guys, I'm back. I think I found one. This one, see, it has Spice file. If you click on it, you'll notice that it just gives it to you. Well, you can get this one of two ways. You can either cut and paste this into Notepad, or you can just right click on it and choose Save Link As. Same thing. Now this comes out as a .SPI. Spice will be able to read that as well. Sometimes I will go ahead and just rename them .CIR, just because I like the .CIR file. It really doesn't change the file at all, but you can keep the SPI, that's fine, but just know that you can do that. Some files, there'll be file extensions that LTSpice technically doesn't recognize. Well, just if you can, it's just text. It's all just text. So if you just change it to .CIR or SPI or something that it does recognize, 9 times out of 10 your model will work. So just know that kind of little trick that you can do. So anyway, so we'll download that. And now, let's see if I can open it. Here it is. Yep, looks like it's going to. And this one is drain gate source, is how its node goes. And so this guy has a subcircuits all the way up here. But see, it is with 1, 2, and 3, it's drain gate source. So like I said, again, I can take and right click on it and just say create symbol right off the bat, and it'll create me a square. Or I can use I can't remember, I don't know if I have one. Well, I could create the symbol if I want to. I think I'm going to do symbol creation for another day. We may do symbol creation in another movie for this guy, but just to show you that this does work, if we right click on this and say create symbol, yes, we've got 1, 2, and 3, and we know that that's drain gate source. So let's give it a shot. Auto generated, there it is. Let me zoom in a little bit. We said drain gate source, so it was drain gate source. Okay, I remember that. Drain gate source. So let's just do a simple circuit. That's the source. This is the drain. And then this is going to be the gate. Just duplicate that, put there, put that down there. Okay. 0. Start this. Let's do 1 ohm and 12 volts. So we should be able to get 12 amps through this thing. Okay. So anyway, so now I'll hit, where are we at? Hit go here. No, 20 millis is fine. Oh, good grief. Good grief. What a pain. Alright, so if we click on current, we have 0, which it should be 0 because we have 0 volts on the gate. So now, we click on this and change it to, I don't know, 12 volts. Say, we hit go, and we get about 8 amps. Well, that's because these, at least this one, I believe, I'd have to probably look into the data sheet, but these take 20 volts VGS max, so they take probably about 15 volts to get them to come all the way on. Yeah, it's about 15 volts to get them to come all the way on, and it says that in the data sheet. I've worked with these types before. But anyway, so there you go. So there's on, 0, and off. So there you go. So now our model works. And again, I'll show you price symbol creation. Since I downloaded this one, I'll show you symbol creation in another video. I'll preview our next video and how to link them all up. Oh, first of all, another thing. I wanted to show you that deal about like using the diode symbol. If your diode's not in this list and you download one, well, there's no, there's no place, there's no attributes box like there is, when you have something like this one, you click on it, it brings up this box. Well, I get this box instead. I don't want this box. I want the other one. I want to be able to type it in. Well, if you hold down on the on the control key, I believe. There it is. If you hold down the control key, that's what I'm doing. I'm holding down control, and then right click again. Now you'll get that box, and you can change it. You can change that to whatever value you want, and then do the .lib thing and everything, and you still utilize the symbol, but change, instead of having to pick from a list, a library list, if you holding down control and right click, now you can change it to whatever you want and still use the diode symbol. So there you go. That's true with anything like capacitors. Capacitors, same way. They'll have, of course, capacitors you can type in the capacitance, so that's not really a problem. Transistors. Let's say NMOS. So like here's the NMOS. I would use this symbol for this guy. I think the deal's the same, but it doesn't show. I don't know why. I like being able to see it, but this has an internal diode due to the construction of it. It's like any other. Of course, they're not going to show it, but any other type of a power, usually the power MOS type stuff, will have an internal diode where the anode is at the source and the cathode is at the drain, and it's just inherent to how they build it. It creates a diode barrier, creates a PN junction right there. So I don't like using this symbol and doing our control and then right click and then changing it, because with power FETs they have that diode, and I like to be reminded by visually reminded that diode's there, just so I don't run into trouble later. But you guys do what you want. There is no reason for it. That's just my own personal kind of thing that keeps me from getting tripped up. But if you guys might as well, just if you want to use this symbol and you can remember that that's there, then by all means use that symbol. There's nothing that keeps you from changing this value to whatever and then putting in your .lib path to the circuit file or the SPI file or whatever. Nothing that keeps you from doing that. So just know that that's there. You can hold down control and right click, and then you can use any symbol as a generic symbol if you want to. You don't have to be secluded to, you can only pick these, or like this, you can only pick these, So keep that in mind. So anyway, that's basically our quick tutorial on how to do subcircuits and how to import things. Feel free to comment, leave any questions that you might have. I'll try to get back to you as fast as I possibly can. If I don't, bear with me. I've got a lot going on right now, but I'll try to get back to you as quick as possible, because sometimes I can't cover everything in a video, like all the manufacturers' sites, because different manufacturers have different ways of doing things. Some of those files you'll download, they'll say that it's a SPICE file, and it'll be a .lib file, and it looks like it's got 15, 20 different subcircuits in it, and that's fine too. What you would do in that case is you would pick the one that's yours, because a lot of times they'll lump a whole family of, especially with FETs, they'll lump a whole family of FETs together, and they'll just have multiple subcircuit in one file, just tons of them. All you do is the same thing. Whichever one you want that is the right part number that you're looking at, just right click on it and choose create symbol, or highlight that one's name, copy it, and then paste it in to your deal, or whichever method you want to use, whether you create the symbol or use an existing symbol and cut and paste the name. But just make sure you're getting that part number that you want among the many that might be in that file. So I know that's true with Infineon. Infineon's they do libraries of components, because especially a lot of their planar MOS. The trench MOS, I don't think they do as much, but I think they're individual. But the planar MOS will come lumped into library files. And so that's what you do there. But kind of things like that, you guys will probably run into. If you have questions, just go ahead and shoot me a comment or whatever, and I'll try to help you out with it. Because like I said, they come in a variety of different flavors. But again, it's all just like ASCII text. So whether it's a .lib or .spi or .cir or there's like an S something, it's not SPI, but it's like something else, SPC or something like that. No matter what file extension it has, like I said, it's just text. You can always resave it or rename it to something that LTSpice will recognize, because it's just text. Or you can even just cut and paste it into Notepad and save it as a .cir or SPI or whatever LTSpice recognizes. So keep that all in mind. So have fun, ladies and gentlemen. Hope these tutorials help. I've been getting some pretty good feedback, people saying that these have been helpful, so I'm glad. Any questions or any places you get stuck, please comment or send me messages. Thank you very much, guys. Take care.